Hello everyone, today let's solve the problem number 297, serialize and deserialize the binary tree. Right, so what the question states here, we have to design an algorithm to serialize and deserialize the binary tree. Right, so what does the serialization here, what does the term deserialize and serialize mean? Let's try to understand that one. Right, so the serialization converts a binary tree into the string. So what does serialization do here? It converts the binary tree into the string. And what does deserialize do? And deserialization reconstructs the original tree from the string, right? So they have asked us to serialize and deserialize, which means we have to convert the binary tree into a string. That's what serialization means. And deserialization means we have to reconstruct the original tree from the string, right? I hope this is clear. I'll read this one again. This itself is the question and try to understand this one, right? So this is very important. Serialization means converting the binary tree into the string, right? So deserialization means reconstructing the original tree from the string, right? So that's what serialization and deserialization mean here, right? So the input or output format follows the Leetcode's format but can be designed independently. That's what they have given here. So simple to understand, right? So the same output that we need to get here in case of, so whatever the input that we give, the same output, because when we serialize it will be converted into string. When we deserialize it will be converted back to the this one original binary tree, right? So here 1 2 3 null null 4 5 they have given. So the output that we need to get here is same 1 2 3 null null 4 5, right? So let's come to the second example here. Empty this one we have empty array, we have the output should be empty array itself, right? So that's what they have given. Wonderful examples just for the sake of understanding. I hope the question is completely clear. What we need to do is completely clear as well, right? So first let's discuss the approach followed by the edge cases one by one, and then let's discuss the then let's write the code and discuss the complexities for the code that we have written. Initially, let's discuss the approach first. Let me clean this up first. Just give me a second here. So yeah. So let's discuss the So the first thing that we need to note down here is we will be going with the BFS level order traversal using queue. We will be making use of the breadth first search level order traversal using the queue, right? So just keep this in mind. I have considered the same first example that they have given in the question, right? So we have already discussed this one. So as we are serializing and deserializing, the output, whatever the input that we give, the same output that we need to get, right? So I hope this is clear. So we have already discussed this one. I hope this is clear, right? So this is fine. So let's move on with the step-by-step execution. First one is serialization part. Let's discuss this one, right? So first we will use the level order traversal, BFS with the queue. We know this one, right? We will be making use of the level order traversal, nothing but BFS with queue, right? So we will start from the root 1 and append it to the result. First we will start from the root 1 and first we will append this one to the result. This is fine. I hope this is clear. We will process left 2 and right 3, right? So as we are going with the level order traversal, first this is the first level, right? So then we will append 2 and 3. This is second level. So this we will append it to the result and this is second level, right? Next we will append this one and this will be, we will be adding that one to the result or appending that one to the result, which is of level 3 basically, right? So that's what we will be doing here. We will process left 2 and right 3. It will be 1 2 3 in this case. So 2 has no children, so we will be adding here null 1 2 3 null in this case. So this one I am speaking of. So 2 is having no children, right? So in this case what we will do, we will go with null and null, because this at the level 3 is having children, which is 4 and 5, right? Now we have 1 2 3 null, then we will move on to the 3 basically. We are done with 2, then we are move on, then we'll move on with 3 basically. 3 is having the children 4 and 5. We will append that one to the result and result at third level. Right, see here 3 has children 4 and 5. So now it will be 1 2 3 null 4 5. 4 and 5 have no children, so now we will stop. 1 2 3 null 4 5 null it will be, right? So null we will not be considering this one because both doesn't have. So here, let me come here, this one. 4 and 5, both the values doesn't have the children here, right? So we'll not give null here. We don't have the next level at all, right? So if 5 had children, then we would have considered null for 4, or if 4 had children, then we would have considered 5, right? So in this case, we will ignore this one, right? We'll ignore this one. So main output will be 1 2 3 null null 4 5. Just remember this one, right? So we have serialized successfully. Let's come to the deserialization part. Serialize means we have successfully converted the input to the string, right? So we have successfully converted the binary tree into the string. Let's come to the deserialization part here. We will be making use of the queue basically. Why will be making use of the queue? Because we have to reconstruct the binary tree, right? So to reconstruct the tree, we'll be making use of the queue. We will start from the 1. So this one, when I say 1, this one I'm speaking of. Again, we are starting from the 1 here, right? So we'll start from 1, we'll create true node. Tree node. This is fine. So it is easy to understand. 2 is assigned as left child and 3 as right. So 2 is assigned as left child and we have 1 2 3 null null 4 5, right? So 1 tree node, this one 2 will be assigned as left, this one subtree, and 3 will be assigned as right child or right subtree, right? This is fine. So next, 3's left child is this one. 3's left child is 4 and right is 5. 3's left child is 4 and right is 5. This one we have to. 3's left child is 4 and right is 5. And this one we have null null, we will ignore. And this is null as well. For 4 and 5, this is null as well, right? So this is null as well. We will return the reconstructed tree. Nothing but in this case, 1 2 3. What we got here? 1 2 3. So this one will be null null and 4 and 5, right? So 1 2 3 null null 4 and 5. That's what we got as output here when we return the reconstructed tree. So here, let me come here. This will be the final output we got, right? So this is the final output we got basically 1 2 3 null null 4 5. So this is equivalent to the output that they have given for the first example. Here you can clearly see 1 2 3 null null 4 5. So our approach works absolutely correct in this case. Our approach works absolutely correct in this case, right? So now we are completely familiar with the approach. As we are completely familiar with the approach, let's discuss the edge cases very quickly. Let's discuss the edge cases quickly. So let me come to the first edge case here. The first edge case is for this one, empty tree, right? So here you can clearly see we have root null. Output will be null as well, right? So this is for the empty tree. So the second one, tree with a single node. We have 5. We are returning 5 null null. So basically, after deserializing, it will be 5 itself. So it will be only 5, right? So this is fine. Let's move on with the third edge case here. This one, tree with the only left children. Here we have 1 2 null 3, right? So this is after serializing, and this one becomes basically 1 2 null 3 at the end. So output will be 1 2 null 3 itself, right? This will be 1 2 null and 3 itself. So after the output is main output is this one. So this is after serializing, right? This is fine. Let's move on with the fourth edge case, tree with only right children. Here 1 null 2 null 3, right skewed. Basically this is left skewed tree and this is right skewed tree, right? So we have solved enough problems to understand the right and left skewed tree by now, right? So root 1 null 2 null 3 we have. So the output that we need to get here is 1 null 2 null 3 null null. So this is after the serialization. After deserialization, we get 1 null 2 null 3 basically, right? So this is the main output. This is fine. So these are the 4 edge cases that we need to consider here, right? The first one is for the empty tree. The second one is for the tree with single node. The third one is for the tree with only left children, and the fourth one is for tree with only right children. These are the 4 edge cases that we considered, right? So that we need to keep in mind. Sorry. So now we are completely familiar with the edge cases as well as the approach. We are good to write the code. Let's start writing the code. So here first let's go with the serialize function, right? So the edge case we discussed, we have already discussed this edge case. Basically the base case, if tree is empty then we have to return null, right? So this one I can write in this way: if root equals null, then we have to return null. So within the strings we have to give, right? So we are converting the input in the form of strings basically, or the binary tree in the form of string in the serialization. This is fine. So that is the reason I have given null in the string, right? So the next step here is we'll be making use of the string builder. Why? We have to store the serialized output somewhere, right? So that is the reason I'll be making use of the string builder, right? So I'll just go with here. Just give me a second here. String builder. Sp here. This is equal to new string builder. This is fine. Next step is we will be making use of the queue for the level order traversal. We will be making use of the queue for the level order traversal. We are going with the BFS, right? BFS with level order traversal. So let's make use of the queue for the level order traversal. I'll just give here, as we are dealing with the trees, let me go with tree node here. So let me make use of the variable queue here. This will be new linked list. This is fine. So the next step is we have to add the first thing, we have to add the root to queue. So I'll just make use of the offer here, offer property, right? I'll just make use of the offer property to add the root here in this case, right? This is fine. So the next step here is we have to remove the node from queue for processing. We have to only proceed if the queue is not empty, right? So let me make use of the while loop here. First let me give this one, while queue is not empty here. So this one, let me remove one I. This is fine. This is fine. Within this while loop, we have to remove the node from the queue, right? So we need to remove the node from the queue for processing. I'll just give here tree node equals, I'll be making use of the poll property, right? For the remove. For adding, I have made use of the offer property. I'll be going with a poll here in this case. We have to remove the node from the queue for processing. So this line is, this is it. So the next step here is we have to append the null for the missing children, right? So that's what they have given here. So for the missing children here in this case, just give me a second here, we have to append the null for the missing children here in this case, right? So that's what we have to articulate the same thing in the form of code. We have discussed this one several times during the approach. The same we have to articulate that one in the form of code, right? So if node equals null, then what we will do, I'll just go with sb dot append here in this case. So this will be null within the strings as we are serializing. So I'll just give here a comma. This is fine. So we are just appending the null for the missing children, and we have to skip to the next iteration. For skipping, I'll just make use of the continue keyword. This is fine. So let's move on with the next step here. Let's append the node value to the result first. So we have to append the node value to the result. Also, we have to add left and right child to the queue. These three things we have to do, right? So let's do that one quickly. First, let's append the node value to the result. So I'll just give here sp dot append. What we are appending? Value of the node. So I'll just give you a node dot value. So let me make use of the append keyword here. So I'll just give comma here. This is fine. So let's add the left and right child to the queue. For adding, I'll just make use of the offer here. This is fine. Queue dot offer. First one, left. We are adding the left child right here. This is fine. I'll just copy the same thing and make the necessary changes. We have to add the right child as well. So instead of left, I'll just give here right. This is fine. So the next step here is we need to return the serialized tree as a string. The final step within the serialization is finally we have to return the serialized tree as a string, right? So I'll just give here return sb. Let's convert this one by making use of toString property. This is fine. So this is it for the serialization, right? So this is it for the serialization. Let me format this one once. I hope the serialization part is clear, easy to understand, right? So let's go with the deserialize deserialize function now. Let's continue with the deserialize function. So here again, if the output is null, then we have to return the empty tree. Now in the deserialization part, what we are doing, we are converting the string back to the original binary tree, right? So the first step here is, if input is null, then we have to return the empty tree. So I'll just give here if data dot equals of null here in this case. So then what I'll do, let's return null here in this case, right? This is fine. So the next step here is, we will split the serialized string into the array. So we have to split the serialized string into the array so that we can make use of the queue for the tree construction, right? So first let's split the serialized string into the array. So I'll just give here in this case string values. Well, we are splitting right here. I'll just go with the data dot split. So we have just made use of the comma. I'll just give comma. We're just splitting right based on the comma. This is fine. So we are splitting serialized string into the array currently. After doing that, we have to make use of the queue for the tree reconstruction. We have discussed this one several times in the approach. So I'll just go with queue here. So as we are dealing with the tree, I'll just give the type tree node here. This is fine. Let me make use of variable queue here in this case. This will be new linked list. This is fine. I hope this step is fine. So next step is, let's create the root node. So to create the root node, let me define here type this one tree node. This will be, we are creating the root node, right? I'll just give here new tree node of, so here this will be, I'll give integer dot, let me make use of the %, right? % of, so this I'll just give values of 0. This is fine. I hope this is clear, right? So the next step is, we have to, after creating the root node, we have to add the root to the queue initially. So again, you would have already guessed, we will be making use of the offer property, right? To add this. This will be queue dot offer of, we are adding the root, right? So let me mention root here. This is fine. So let's move on with the iteration part. We have to get the parent node from the queue, right? So let me quickly write here int I equals 1, I less than length of the values here in this case, and let me increment I here. So we have to just get the parent node from the queue within the for loop. So I'll just go with here tree node. So let me initialize, assign the parent to, so we have to remove the value, right? So I'll just go with the poll property here. Means we have to get the parent node we are getting the parent node from the queue. Next step, after getting the parent node from queue, we have to create the left child and right child, right? So we have discussed this one. So first we got the root node, then we have to get the left and right child, then we have to get the children of it, right? If it is present, that's what we need to do. Then let's get the left child and right child, right? So as we are dealing with the BFS, once we get the left child and right child, it is fine. So we have to write the code for getting the left and right child. So first let's write the code for creating the left child. So here it's simple. Let's go with the simple if condition here. If not of values of iterated value of the values is not equals to null, means if the value is present, means if right and left child is present, if its value is not null, means if the left child is present, right? So then what we will do, I'll just give here parent dot left equals new tree node of, so let me give here integer dot parse int of values of I. This is fine. This is simple to understand, right? We are just creating the left child here. After creating the left child, we have to add the left child to the queue. Again, we'll be making use of the offer property here. Simple. queue dot offer here of this one, parent dot left here on this case. So same thing we have to do for the right child as well. Let me copy this one and make the necessary changes here, right? So just come here in this case. So this remains same. So this actually varies, right? So this is for the right child. Oh, this varies completely actually. Just give me a second here. If this one I, so this is less than values of values dot length in this case. This is fine, and not of this one. Values of I means iterated value of the values, which is equals to null. So just give me a second. This is fine. If it is not equal to null, right here, basically that's what we are doing here. This is fine. So then instead of the parent dot left here, let me change this one to right, as we have to create the right child here. So this is a new tree node of integer dot person values of I. This remains same basically. This is fine. So then after creating the right child in the line number 45, in the line number 46 we have to add the right child to the queue. Same thing. So here this remains same, queue dot offer of parent dot left. Instead of left, I'll just go with right, as we are dealing with the right child, right? So we have successfully created the right child and we have added the right child to the queue, right? So this is it for the coding part. The last thing is we have to return the reconstructed tree, right? So we have to return the reconstructed tree. So let me come here. Let me give you a reconstructed tree means we have to return the root in this case, right? So in our case, so this is it for the code. I hope the code is completely clear, easy to understand, right? We went with step by step. Basically first we went with serialization, second we went with deserialization. Easy to understand, right? So let me hit the run button now. So just give me a second. Here we have the error. What last executed output we are getting? This one, number or format expression for input string null. So this is saying us this one, number for input string null. So here let's come to line number 29. You can clearly see here, if data dot equals I have given null, I have misspelled here. This one has to be null, right? So let me run the code again. I hope this works this time. Let's see. So yeah, now we can clearly see the sample test cases are getting passed. Let me hit the submit button quickly. So you can clearly see here all the test cases are getting passed. Means the code works absolutely correct on this case. I had made one mistake here. So I had misspelled null here, right? So I had misspelled null in the line number 29. So it was giving us wrong output basically. So that's fine. Now all the test cases are getting passed. Means the code works absolutely correct on this case, right? So let's quickly discuss the complexities for the code that we have written. So the approach that we went with here is BFS level order traversal using queue. We know this one, right? So what would be the time complexity here? So the time complexity for the serialization and the deserialization, for both it would be big of n. For the serialization part, we are visiting each node exactly once. You can clearly see here we are making use of the while loop, right? So we are visiting the this one, each node exactly once. And for the deserialization part, we are processing the node exactly once for loop. You can clearly see here, right? So overall time complexity for both serialization and deserialization is big of n. I'll just write here big of n in this case. You can just consider big of n for the serialization and big of n for the deserialization as well. Overall it will be big of n, right? So what would be the space complexity here? The space complexity would be big of n as well. Why it is big of n here? In this case, we are storing the tree nodes in the queue during the BFS traversal. We are storing the this one tree nodes in the queue using BFS traversal. We are making use of the queue at every step, right? So we have seen this one. So here queue. So everywhere we are making use of the queue. because we are storing the tree nodes in the queue itself during the BFS traversal. This is fine. So this is the reason overall space complexity would be big of n as well. So the time complexity and the space complexity for the code that we have written is big of n in this case. I hope the complexities are completely clear, and I hope whatever the code that we have written is completely clear as well. Right? For now, this is it. Thanks for watching, guys.